Hello and welcome back to Proofwriting 101. Today we're going to prove this iconic summation formula, which says that the sum of the squares of the first n natural numbers is equal to this fraction. So let's do it. As usual, when dealing with natural numbers, proof by induction is usually good strategy. So first, we have our base case. We've got to prove this formula is true if n equals 1. Well, if n equals 1, the sum on the left just becomes 1 squared. And then this expression on the right becomes 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. I've got to ask, is this true? Yes, it is, because this is just 1. And then this expression, this is 1 times 2 times 3, which is 6, all over 6. So this is 1 as well. So this is true. Okay. And now our inductive step. What we want to do is we assume that this guy is true for some fixed arbitrary n, which is a positive integer. And what we want to do is we want to show that if you add all the terms to n plus 1, that the formula is true for n plus 1 as well. How do you do that? Well, this sum on the left can be rewritten. It's 1 squared plus 2 squared plus dot 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 plus n squared plus n plus 1 squared. And now what is this guy? Well, by an inductive hypothesis, this is the same as this fraction. So we can replace this part with a fraction. Let's copy paste that. And then the right side, well, we can simplify this monstrosity a little bit. We get n plus 1 times n plus 2 plus 2n plus 3 all over 6, okay? All right, and now for our next step, to get rid of ugly fractions, why don't we just multiply both sides of this equation by 6? So if we do that, we get n times n plus 1 times 2n plus 1 plus 6 times n plus 1 squared is equal to this numerator here. Copy paste that. Okay, so let's simplify this. Let's see, what do we get here? I'll FOIL this part first. We get 2n squared plus 3n plus 1. And then this part, I'll FOIL the inside first. We get n squared plus 2n plus 1. Okay, then what about the right side here? I'll leave the n plus 1 as it is for now, and I'll FOIL this. Let's see, we get 2n squared plus 7n plus 6. Okay, now we can simplify this even more. Let's distribute the n. We get 2n cubed plus 3n squared plus n. And then for this part, distribute the 6. We get 6n squared plus 12n plus 6. Okay, and this part simplifies too. We got to FOIL this with this. So we get, I'll distribute the n to all these first. We get 2n cubed plus 7n squared plus 6n. And now I'll distribute the 1. We get 2n squared plus 7n plus 6. Okay. Oh, that's pretty long. Okay. And we'll can simplify this by combining like terms. It's so long it's even cut off the screen, goodness gracious. But we get, combine the cube terms, we get 2n cubed. Combine the square terms, we get 9n squared. Combine the n terms, we get 13n. and combine the only constant term 6. Okay, what about the right-hand side? Well, we get for the n cubed terms, we have 2n cubed. For the n squared terms, we have 9n squared. For the n terms, we have 13n. And for the constant term, we have 6. And look, these are the same. Okay, so we're done. So we prove that it's true for n plus 1. And by the principle of induction, we're done.